Hello everyone, good evening again. This is AP Biology and we're going to look at population ecology study questions. Again, these are going to be from my personal class, AP Biology. We might have different notes than you guys who are looking at this video for help. In case we do, please feel free to look any of these answers, do your own research from your own textbook or your own notes. And this is just going to be a brief overview, so it's always beneficial to explore and reach out for more information on any of these. They'll only benefit you and won't hurt. All right, let's get started. Okay, so population, we have to list two ways organisms enter and leave populations. And first of all, before we start, a population is all the members of one species living in the same place at the same time. So basically, like all the white deer in Texas, all the white-tailed deer in Texas, all the sparrows in my backyard, specifically this morning, like that. Okay, so into a population, we have birth and immigration. And out of a population, we have death and emigration. Immigration is coming in. Emigration is going out. The value of R is different for the two curves. So this deals with the JCurve. We could see the rate. The R is the per capita rate of increase. We see here this has a better rate of increase. It's larger. It's 1.0. This one is half that rate. Over the generations, this one would increase in population number of organisms more than this would. Just means that how many offspring or individuals were in that population. So you could see this lesser rate. There must be lesser individuals or organisms. But in this population here of this species, you can see there's a lot of them. Therefore, the rate is higher. The JCurve model, or the exponential growth model, assumes that there aren't any limiting factors. There's no resource limitations. If R was 0.0938, what does that tell you about the population? Well, we know based on this graph, let's pretend that 0.0938 was on here. It'd be somewhere between 1.0 and 0.5, just closer to 1.0. This would mean that it took less generations for it to get up into these larger population numbers. This also means if R was positive or greater than 0, this means this population is growing. If it was less than 0, that means the population is shrinking. And if it was equal to 0, that means there's a holding pattern in the population. Describe the difference in the two formulas. I'm guessing it's talking about the logistic function and just the JCurve function. So DNDT, dn over dt is the change in the number of individuals over the change in time. We have the rate R and the number n. That's the starting value, I believe. In the logistic function, we have dn over dt again is equal to R. It's that rate. N, which is the current number, the population. Then we have it over this fraction over here, in parentheses K, which is the carrying capacity, which we'll see is this line right here, the dotted line where this graph isn't touching it. It wants to go above it, but this is basically like a bar that can't pass in the thing. This could be a resource limitation for logistics. Carrying capacity minus N, again, that's the current number, the population, and all of that divided by K, so it's dn over dt equals Rn times the fraction. The numerator would be K minus N, and the denominator would be just N. If N is a large value, how does this affect the population growth in the carrying capacity formula? Well, let's say in the example, the carrying capacity is 1,000. That's the number in the population that it's like its max limit. If N was really close to that number, that means there isn't much room for growth. and so therefore we'd get a low number for DNDT. Mark and recapture is used to estimate populations, counting organisms. We get a small sample, we put it back to the population, and we continue from there. The equation for this is a fraction, where in the numerator we take the number first marked and we multiply it by the total in the second catch, and then we divide this number where it's the number first marked times the total in the second catch over the number marked in the second catch. And we could use this to find the density of a given region. Let's say that the number in the population first mark was 15, and then the total in the second catch was 18, and then the number marked in the second catch was just 3, that would be 90, and then let's say that this area was 10,000 square miles, versus the second area where it's 19 for the number first marked, times 29, which is the total in the second catch, over 3, which is the number marked in the second catch. That would be 183 and 2/3 in an area of 650,000 square miles. And we could see the one that was 90 over 10,000 square miles would have the higher population density. The possible drawbacks of mark and recapture is, of course, it's an estimate, so maybe the population is just large, maybe other factors like that there aren't all in that same area where you're doing these estimates. We also have different population distributions, so that could also be it as well. Dispersions, which are clumped, and that's like oases or trees. And we also have uniform, which is the gulls in the neat rows. We also have the random dispersion of grass. Survivorship curves. Life tables, reproduction, survivorship curves. So we have the survivorship curves, which are part of demographics, which is the study of population's vital stats. The type 1 curves, okay, let's pretend we have a graph here. Let's just use, I think we could draw on here. Let's quickly draw this. Okay, and we're going to be using a freestyle scribble. Okay, so we have a graph here, survivorship curves. Okay, so we have this one right here. Let's say this is this is going to be the number, the survivability, and we could say this is, I think age is at the bottom here. So this is type 1. This is type 1, where population's doing really good when it's young, but as it gets older, this is where there's going to be a dip. There's less survivability. So this one is less survivability when it's old down here. So like, let's say this is 100 years old. Less survivability down there than up to here. Now we also have type 2, where there's a uniform decline. This would be animals like lizards. This one up here would be like hippos. So lizards, it doesn't matter their age, they're all going to decline at the same rate. On type 3, we have the young dying at a higher rate than the old. Should look like that. These would be fish, because they have very little competition when they're small hatchlings, and there's a multitude of fish that when they're babies, not all of them survive. A good majority of them don't survive. So when the young die, that's type 3. This is type 2, steady decline, and then type 1 is when as they get older, there's more decline. All right, our next one is parental care and life history traits. parental care is the number of offspring relates to the amount of parental care. The parents survive in winter, and birds with smaller number of offspring. There's less stress, there's less energy to feed all those hungry mouths. Make a table showing the contrast between 6 features of R-selected organisms against K-selected. R-selected is a high rate per capita population growth. There's poor competition. These include weeds, insects, short lifespan organisms, flies. K-selected is more stable populations, more stable species that could adapt near the carrying capacity. We have oak trees in here, whales, hippos, even humans. What does the mortality rate look like on a graph of density dependent, density independent, inverse density dependent factors? Density dependent is when the mortality rate varies according to population density. So think like a big city and a sparse town. In the big city, there's a chance of the higher spread of, right now we're dealing with the coronavirus. We could use that as an example of density dependent. So in these densely populated areas, there's a higher chance of the mortality rate versus the sparse town. Either situation, please wear a mask. Of course, density independent is when the mortality rate is unaffected by population density. So think of a fire striking a forest. That's not dependent on the population density there. It's going to kill all the wildlife wherever the amount there in that area at that given time when the fire occurred. It's not going to pertain if there's more deer in the area or not. It's just going to wipe it out in that given specific time frame. Inverse density dependent is when the mortality rate decreases as population density increases. So an example of this would be a lion would kill 1 wildebeest per week, but this is a steady rate of decline because it's only 1 wildebeest per week. Wildebeest will keep on having babies, reproducing, and then their numbers would still grow. And yes, the lion would be taking off 1 per week, but it's a steady, small rate compared to their rate of growth. Age structure diagrams. So this is human population. Now we were given an example of humans. In West Africa, mostly we're young people, so that would be massive growth. While in Western Europe, on the other hand, we have a larger population of older people from the older ages, and there'd be a negative rate, and there'd be lesser growth. The steps of a demographic transition. We had to look that up. I do not remember in the PowerPoint we were given that these were in there. So stage 1, high population growth potential. Stage 2, population explosion. Stage 3, population growth starts off to level. Stage 4, stationary population. Stage 5, further changes in birth rates. Please read more about this. Again, I don't think it was in the notes that we were personally given. So just please look it up online. If you need more information on any of these topics, we did 2 other videos other than this one. And then the last question was TFR. It's the total fertility rate. And there's just a lot more information on here that I don't believe was in the PowerPoint either. So that's another one that we would like to look at. All right, I hope this helped and have a good day.